We're going to look at the mole, which is a measurement of matter. 1 mole is defined as 6.02 times 10 to the 23rd representative particles of that substance. And the 6.02 times 10 to the 23rd is referred to as Avogadro's number. Representative particle can refer to atoms if we're talking about an element. So for example, in 1 mole of iron, there are 6.02 times 10 to the 23rd atoms of iron. If you have a diatomic element or a molecular compound, the representative particle is the molecule. So for example, 1 mole of water would contain 6.02 times 10 to the 23rd molecules of water. And then finally, the representative particle can be a formula unit if it's an ionic compound with a metal in it. So for example, 1 mole of calcium chloride is equal to 6.02 times 10 to the 23rd formula units. So Avogadro's number can refer to atoms or molecules or formula units, and it depends on the substance. Let's look at some problems. How many moles is 2.8 times 10 to the 24th atoms of silicon? So we're going to start there. Silicon is an element, so the representative particle is the atom. So that means there are 6.02 times 10 to the 23rd atoms in 1 mole of silicon. We'll cancel out the atoms like that. Divide by Avogadro's number, and we get the amount of moles. At 4.65. This next example, we have 2.17 times 10 to the 23rd representative particles of bromine. Bromine is diatomic. It's Br2. So the representative particle for a diatomic molecule is the molecule. So there are 2.17 10 to the 23rd molecules of bromine, and I want to go from molecules to moles. Since the representative particle is the molecule, that means there are 6.02 10 to the 23rd molecules in a mole. Same number as the previous problem, but my unit is now molecules instead of atoms like it was with silicon. But mathematically, we're going to solve it the same way. Divide by Avogadro's number. So 0.36 moles. If we're converting moles to the number of particles, we first have to determine the number of representative particles, and then we're going to multiply the number of representative particles by the number of atoms in each molecule. Let's look at a couple examples there. Start with what we're given. We have 1.14 moles of SO3. We're looking for atoms. We're going to go from moles back to the representative particle. Now SO3 is a molecule, so there are 6.02 10 to the 23rd molecules in a mole, because this is a nonmetal compound. That will get me to molecules. I want to know how many atoms there are. Well, in SO3, there's 1 sulfur and 3 oxygen, so the total number of atoms is 4 atoms in 1 molecule of SO3. So I went from moles to the representative particle, which was molecules, and then there are 4 atoms in 1 molecule. So the total number of atoms, 2.75 10 to the 24th atoms in this molecule. How many atoms are in 2.12 moles of C3H8. Start with the moles. Go from moles to the representative particle, which again, this is a non-metal compound, so the representative particle is the molecule. So 6.02, 10 to the 23rd molecules in 1 mole. How many atoms are there? Well, in 1 molecule, the total number of atoms, 3 carbon, 8 hydrogen, so that would be 11 atoms in 1 molecule. Very similar to the previous example. So 1.4, 10 to the 25th atoms in 2.12 moles. One more example along those lines. How many atoms of oxygen are in 3.65 moles of this compound? So we're going to go from moles back to the representative particle, which again is a molecule because this is a compound composed entirely of nonmetals. So moles to molecules. How many atoms of oxygen are there? Well, in this compound, there are 11 atoms of oxygen in 1 molecule. I don't want the total number of atoms, just oxygen. So when I multiply across, I get 2.42, 10 to the 25th atoms of oxygen. The atomic mass of an element is expressed in atomic mass units, which is a very small unit. That's not practical for us. We need to use grams. So grams are more convenient to work with, and we're going to convert AMUs to the relative scale of masses in grams. We're going to go back to the periodic table to get what's known as the molar mass. For example, the molar mass of oxygen is 16.0 grams, and the 16.0 comes from the periodic table. Molar mass of carbon is 12.0 grams. Again, 12.0 from the periodic table. And I always round those molar masses to the tenths place, so to 1 decimal place. To find the molar mass of a compound, you have to know the formula. So let's look at an example where you're given the formula and we're asked to find the molar mass. The first one, what is the molar mass of glucose? Here's what you do. You have 3 elements in that compound. We'll start with carbon. There are 6 carbon. Multiply by the molar mass of carbon from the periodic table. And if you look in the periodic table, molar mass, 12.0. Round to 1 place after the decimal. So 6 times 12 gives you 72. Hydrogen. There are 12 hydrogen in glucose. Times the molar mass of hydrogen from the periodic table is 1.0. Oxygen. There are 6 oxygen times the molar mass of oxygen from the periodic table, rounded to 1 decimal place, 16.0. And then we simply add those together to get the total molar mass of the compound glucose. So 180.0, again 1 place after the decimal, and the units, grams per mole. So this is the molar mass of glucose. I'm going to skip PCl3. I'm going to go to Al2SO43. You can do it the same way. Aluminum, sulfur, oxygen. Those are the 3 elements. I have 2 aluminum times the molar mass of aluminum is 27.0. So 54. Sulfur. 3 sulfur, because we multiply through the parentheses, times the molar mass of sulfur rounded to 1 decimal place is 32.1. And then oxygen, you multiply through the parentheses, so 12 oxygen times the molar mass and add those together. So the molar mass of the compound aluminum sulfate is 342.3 grams per mole. This last problem I changed up a little bit. I changed the number here. Instead of 1 mole, it's 2.31 moles of sodium hydrogen carbonate. I need to know the formula for sodium hydrogen carbonate. Sodium hydrogen carbonate is CO3. And the charges, sodium's a +1, hydrogen's a +1, and CO3 is a -2. So the charges balance out. So this is the formula for sodium hydrogen carbonate. I need the molar mass of sodium hydrogen carbonate because I want to find the mass in grams of 2.31 moles. And you can get the molar mass in your calculator. Sodium is 23.0, hydrogen is 1.0, carbon is 12.0, and I've got 3 oxygen, so that's 3 times 16.0. But again, you can do all of that in your calculator to get the molar mass. So the molar mass of this compound, when I add those together, is 84 grams per mole. Now I want to know the mass of 2.31 moles. So I'm going to start there, 2.31 moles. I know the molar mass, it's 84 grams in 1 mole. So if I multiply by 84 grams per 1 mole, your moles cancel out. I'm going to get the mass in grams. So 2.31 moles has a mass of 194 grams.